In this screencast, I'll show you how to calculate lens correction models for multicolor confocal stack acquisitions, such that all the color channels are aligned to each other and individual lens distortions are removed. We use existing tools in Fiji and a couple of scripts. I'll guide you through this step by step. Let's first have a look at the data that we're dealing with here. We have here a set of confocal stacks that were required by Janelia's Flylight project for the particular purpose of compensating for lens distortions in their microscopes. We have here one sample set for each scope. These are 6 scopes overall, and we want to compensate for the lens distortion in scope 6. So what are we dealing with? There's a directory data with a lot of LSM files. Each of these LSM files has several channels. I'll show you one of those. And these channels are showing us bead samples. These bead samples are fluorescent over more or less the entire spectrum. So here there's 2 channels. They're not showing exactly the same structure, but approximately the same thing. So they're pretty much comparable across individual channels. And then these samples weren't acquired just as a single 2-dimensional image, but as a, well, this channel is pretty dark, as a Z-stack. So that we have at least one section where the beads are in the focal plane. So the first thing we're going to have to do is to project these acquisitions into single 2D images. In a previous experiment, we figured that the lens distortion is approximately constant across Z layers if the sample doesn't have a lot of different diffraction indices. These samples were required, each stack in 2 different LSM files. One of the LSM files contains 2 channels, and one of them contains 3 channels. The first one with 2 channels is 488 nanometers and 594 nanometers, and the second one is 488 nanometers, 561 nanometers, and 647. So this, for example, is the second stack of that same place with, as you can see here, 3 color channels. All right. So in order to project these individual channels down, we open a script that of purpose in Fiji's script editor. That's this, where you find it, max intensity multi-channel LSM script. And in here, we'll have to change the directory that we're working in. We can copy that from the file browser. Put it in here. Don't forget the trailing slash, because otherwise it's going to break. We'll throw a little exception that it can't find particular files. And then we're running this script, and we'll wait until all images are projected. I can fast forward this. After the script has finished, we should see a lot of additional files in this directory. As we've seen before, they are named by the original file name and then the individual channel projections. This is one example. So now we see that more or less all beads are in the focal plane, which is approximately the place where it's brightest, so the max intensity projection does an okay job here. Alright, now we have to create a TrackEM2 project because we were using the lens correction model available in TrackEM2 to calculate the individual lens corrections for each of the color channels. The TrackEM2 project needs a project folder. We're working on this scope 6, so we can take that directory. And TrackEM2 opens 2 windows. One of them is the canvas window. I'm going to make this a little bit smaller, then we can see something in this. environment here and the main window. In the main window, these two columns are not interesting for us right now, but we're interested in these things here. We will generate a layer in TrackM2, an independent layer for each individual channel. In our acquisition, we have 5 channels. It's actually 4 wavelengths, but the 488 wavelength is present 2 times. And in order to get a better idea of what our lens correction model is eventually doing, we're going to process that as an individual channel twice and then compare the results. So here we add many new layers, 5 in fact, and we're going to skip over the existing one. So we have 5 individual layers that we can scroll through here in the canvas window. Now we're going to import these the files that we generated before into these layers, and I haven't found a reasonable way of automatically selecting them. One should probably write a script to do this. It's not happening so often. I'm doing this manually here. I'm going to have to do it only 5 times because we have only 5 channels. This was the first. And we're going to fast forward here. So now that we've imported all these channels, we see that they have different lookup tables, which is not particularly helpful in this application, and this is going to be the first thing that we're fixing after we have adjusted some project properties. In order to render lens corrected images, we want to have that at the best possible, or at a pretty good precision, and we want it fast, so we increase the mesh size that is used to tessellate the images for rendering, and the number of threads that are running in parallel to generate preview images. Then we click an arbitrary tile and we adjust the images. Let me pop up this dialog here. So we adjust the image filters, which opens this little window. And first thing we do is we use a custom lookup table with the color white instead of the arbitrary colors that the export of that TIFF files has generated. And then we normalize the local contrast to boost the higher frequency information in these images that we're actually interested in. And we apply this to all images in all layers. That's the result of that. So all images are gray. We see the beats prominently everywhere. There's no dark place in any of these images. Close this window again. And now, in order to get a better idea of how the montages look without lens correction, we're going to montage these images first. Do this in the Align menu, montage multiple layers from first to last, using the least squares feature-based method. We're changing the feature extraction parameters such that the minimum image size is 400 pixels and the maximum image size is 900. Something around that range will always work. We reduce the feature descriptor size here to 4, because we know that the images look very similar, so there's not much of a difference expected. We allow a maximal alignment error of 50 pixels. It's probably less, but this is only an upper bound. And we require for each overlapping candidate that at least 20 corresponding points are identified that support a translation. We can check or not check this box. It doesn't make a difference here because we know that none of these images has been imaged twice. The desired transformation for the montage is a translation. We don't have to regularize that anyways and leave everything on the default values. And then we check these upper boxes. because the tiles are roughly in place. We know that because they're all overlapping each other. We don't make a sophisticated test for that. And practically, all of these things don't matter in this application here because we don't deal with independent, not connected montages. So we can have that checked or not. Doesn't really matter. After the montages have been done, it's a good moment to inspect our data sets. And first of all, we want to see whether there are seam problems in the stitching. Let's look at that. It already looks like one. So this is apparently the best thing our montaging pipeline could do, because these images are obviously distorted, and this distortion can be compensated by a sure affine transform. So there's differences in different places across the field of view. And the second thing that you will notice is that as we're scrolling through the channels, they're obviously not aligned. This is not an artifact of the microscope, but only a side effect of the fact that we have generated these montages independently, and we haven't chosen a reference. So they're just floating free in space. So in order to get a better impression of what's going on here, we can align these layers without a reference, because we don't care which one is in the middle, and we do this from first to last. We use 400 to 1200 pixels as the scale space range, and feature descriptor size is again 4 because we're expecting to see approximately the same structure in here. We compare all to all layers, so 5, and we allow a maximal transfer of 200 pixels, which probably is not happening, and we're expecting a translation. And we're seeking for the translation that explains that best. So we're seeing in the range of 6 to 7 to 8,000 features extracted. These feature sets are getting compared and optimized runs, and the channels should be approximately aligned. What we still see is that there are obviously differences across channels that couldn't be compensated for. And this is what we're hoping to compensate now. So the first element to fix is the nonlinear component of the lens distortion. And before we do this, we adjust the size of the canvas. Auto resize canvas layer set. So that we're dealing only with the relevant parts of the field of view. And then we go through our channels one by one. We click as a reference one image that is in the middle. This is a 4x4, 60% overlap calibration data set. So there's no center tile, but any of the close to center tiles is good as a reference. So we click that tile, then we hit Ctrl A to select all the rest, and then we go to patch lens correction to perform nonlinear lens correction. The parameters here are the same as in the SIF feature dialog that you've seen before for montaging. This is where we change things. We expect a very, very small relative transfer error for small clouds of points, so we're assuming everything is relatively smooth. And we want to find all the corresponding sets of points in the image that support at least a rigid transformation, right? So we're not only expecting to find one model because the images are distorted, but maybe several patches that then after distortion would allow us to register them with a single model. So for now, we set this to 5, we set the number of correspondences that we want to see in these sets to 5, the minimum number. And we're expecting at least a rigid transform, so images can shift and rotate relative to each other, which is probably a good approximation what can happen at the periphery of individual tiles. We test multiple of these hypotheses and we want to see them all. We ignore constant background. In this case, is again not very important. And we know that the tiles are roughly in place, so we don't have to compare this tile with that one because they don't overlap. We expect a translation because our stage has only moved by translation, hasn't rotated and tilted or anything like that. And we leave everything else at the default parameters. In the distortion correction dialog, we leave these two places at the default parameters, and we check these two boxes for visualization purposes. So in the log window, we'll see again that this is extracting features for each of the tiles. Then these feature sets are getting matched. See that oftentimes this is not only one hypothesis of corresponding features, it finds up to 4. Then this is the first iteration. Attempt to montage that without a lens correction model. Now, given that montage, the algorithm seeks for a lens correction model that improves upon this montage. And it seems it did, so it brought it from over 2 pixels average displacement to less than 1 pixel. There's not much of a difference for the second iteration. And so the algorithm stops and visualizes the lens correction model. And for visualization purposes, we can save this as channel 1 TIFF, and then we repeat the same operation in the next channel. Center toggle click, Control A, rate, patch, lens correction. And we confirm all the dialogues as they preserve the parameter choices that we did in the first channel. We do that 5 times for each channel independently. So now that we have a lens correction model for each of these montages, we want to visually compare them. There's one thing to note: while the implementation in TrackM calculates montages on the way to get these lens correction models, it doesn't apply them to the montages that we see here in the canvas. So before we can get a visual impression, we will have to do that again. So we montage multiple layers as we did before, 1 to 5. We can stick with the parameter choices that we did before. Alright, so once this is finished, we've seen earlier that we have to align these layers, and this time we do it with an affine transformation, because the independent lens corrections that TrackM estimated rectify all these images up to a unknown affine transformation. So if there is a bias in the images, like the channels are either translated relative to each other, or rotated, or sheared, or scaled, that would have not been accounted for. And in order to have a lens correction that is consistent across all these multiple channels, we will have to now align them using an affine transformation. We can do that with TrackEM to its layer alignment that we used before. We leave all these parameters as we had them earlier. We leave these as we had them earlier. And the only change that we're doing now is that we want to estimate an affine transform, want to regularize them by a translation that goes into the system by a factor of 1%. We again see it extracting features that has slightly increased over the previous run. I don't know why. So we see pixel transfer errors that are higher than what we had before. So now let's, first of all, we can reduce the field of view, auto resize, canvas layer set again, and then as a first thing, let's go into places where tiles are overlapping each other, and then by bringing them to the front or back, we can compare them to overlapping regions. This doesn't seem to work right now. Not exactly sure why. So I'm clicking this tile, and then I move it up and down. And so I was probably confused by the fact that it looks really almost the same. It does so across the entire field of view. And that's actually the situation that we were hoping for. So take this one, bring it up and down. So even in the very periphery of images, the overlap is accurate, almost accurate, so accurate in the subpixel regime. So now we can also scroll through the layers. Fluorescent proteins are not always in the exact same location, but they cluster and accumulate around these beads. And given that, my impression is that the channels are reasonably aligned now. Can actually try to improve upon this by doing this align layers operation again. Goes from first to last, and we can try to if that excludes any of the features that we got earlier, everything else remains the same. Oh, so to me it seems that in the previous run we had included a couple of features that were actually not in the pool of good matches, and now the displacement is significantly smaller, so this alignment is what we're actually wishing for, and that is consistent over all places in the entire field of view. All right. So now, how do we get a hand on these transformations? We can just select the first tile and use Fujit's scripting interpreter. Bean Shell is a good language for these kind of things. We close the log window to make it clear for what's coming up now. And now we can log the transformation, the complete transformation of the first tile that we selected in the current field of view. That's the XML export. We see that this transformation consists of the nonlinear part and the affine transform that brings them all on top of each other. I see. Let me do that for each channel. Such that we have all these transforms exported into the log window. And now we can generate a comparison display to understand a little bit more about these transformations. I'm using one of the other scripts that we generated for this experiment. Put this in here, and then one by one transfer this information into this place here. That's all stuff that we don't care about right now. So this is the first model, and the affine part. The output of this script is a matrix display of this kind. So on one side of the matrix, the upper half, we see color intensity projection of the amplitude and the orientation of the display field across the field of view of one image. This is compared to an identity transform, so this is obviously dominated by some stretch or bias that is not particularly interesting in this case. But this part here of the matrix is interesting because it shows us the relative differences of lens correction models across the individual channels. What we see here is the relative differences plotted into a circle diagram, 2D, so we see where it's going, if there's a shift bias or something like that. And if we zoom into this, we see some interesting things. So here the first two rows and columns are the two 488 beat samples, and we see that the model that we've estimated for these is almost identical, except for some subpixel shift, which is very strongly visible here. Otherwise, this dot would be in the center of this plot. We also see that the differences to the other lenses is a little bit more significant. So this is 2 pixels. The inner circle here has 1 pixel difference. It's good that we did that, because now we have these differences accounted for. Here's a little bit of a shift bias again. And down here, there's also a shift present. There's obviously not so much difference between these two wavelengths, lens models. Alright, so with these exports at hand, we can fix all our confocal stacks, and hopefully stitching and analysis of them will be more meaningful and visually pleasing. Thanks for your attention.